Okay, in this video, we will talk about application of second-order linear differential equation on mechanical vibrations. Okay, so we consider the problem like this. We have a spring here. Okay, this now is with its natural length. Okay, now if you hang some weight here, okay, they will stretch the spring from its natural length to here, then they stop. Okay, so we call this distance L. Okay, so now there is no motion now. That means they achieve the equilibrium position. In the other words, in this case, all the external force add together give you zeros. Okay, now, if we, for example, we pull this weight here. Okay, so for example, we pull this weight here away from its natural length position, then we will release that. We will set the motion. This spring is going to vibrate up and down. Okay, so the question now is we want to answer the question like, for given moment t, where is the block? Okay, what is the velocity of that? So on and so forth. So to answer this question, we need to set up equation. Okay, so we let u here use a function of t, tell you the displacement, in other words, the position of the block. Okay, so at the equilibrium position, we set u equal to 0. Okay, and go downwards. This is a positive u. Okay, now let's describe this motion. Okay, and this motion also followed Newton's second law. Is ma equal to F. Okay, so let's consider the simple case. Only the gravitational force and the restoring force of the spring. The spring want to go back to its natural length. Only those two forces apply on it. Let's consider that simple case. So F here is equal to like two forces, right? So F1 is the gravitational force and F2 is the restoring force of the spring. Okay, since our u, positive u, is pointed down, so F1 here is mg positive, okay, because gravitational force of the same direction as the positive u. Now let's look at the restoring force. Say block here, this is the displacement, is u. Okay, restoring force F2. The spring want to go back to its natural length. Is negative k times displacement. Okay, remember we use u here as a displacement. So if your block is here, what is the restoring force? Is u, which is this displacement, plus L. Okay, u plus L. That's how far away this block from its natural length, which is u plus L. Okay, so we can set up our equation. Our u here, u is a displacement. Then u prime give you the velocity. And u double prime, this will give you velocity. U double prime give you acceleration, right? So the Newton's second law can be written like this. M u double prime. Again, u is a function of time. Tell you where is your block at a given time. Okay, equal to F1 is mg plus F2. Okay, restoring force is always against your position. Okay, they always want to go the opposite. So minus ku minus kl. Okay, what is L? L there U equal to 0 is the equilibrium position. In the other words, in that position, all the forces add together, which is mg and the plus restoring force. Want to go, say, block here. Want to go back to the natural length. So, which is a minus KL equal to MA. At the equilibrium position, the block stay there. So, acceleration is 0. Okay. Therefore, mg minus KL equal to 0. Okay. Therefore, the left hand side only give you k times u. And let's simplify this. This is minus ku plus ku put on the other side equal to 0. So this one is the equation 1 is the equation for the u is the displacement. So if you solve this equation, you're going to find u, which is the displacement, which tell you where your block is for given time t. Okay. Now the things could be more complicated. For example, if this block, this vibration is performed under some oil like this, the block is like sinking in the oil. So you cannot ignore the resistance force, which is also called the damping force. So if you add the third force, a damping force, which is always negative proportional to the velocity. Velocity is u prime. Okay. So if you add damping force, then you put on the other side, you got this equation. Gamma here, u prime plus ku equal to 0. Okay. So equation 2 is with the damping force. Okay. Now if you attach your block with some motor with the other force, then you got another one, even more complicated. Gamma u prime plus ku equal to ft. You have additional external force other than damping force, gravitational force, restoring force. Then you got equation 3. Okay. If Ft equal to 0, we call it the freight vibration. If Ft equal to 0, gamma equal to 0, like vibration described by equation 1, we called undamped free vibration. Okay. Equation 1 described undamped free vibration. Okay, now let's consider this case. First, this is the simplest case. Okay, if we want to find out, we want to solve this vibration problem. In the other words, for given moment t, where is the block, what is the velocity, and so on and so forth. So we need to solve this differential equation here. Find the u, right? Then you can answer the question. Okay. So do we know how to solve this equation? Yes, this is second order linear homogeneous equation. We know how to solve it. So write down is, here is R, okay, not gamma, okay, plus K equal to 0. Okay. So your R square is equal to minus K over M. So your R here is equal to positive or negative square root K over M I. We give a name, okay. Omega 0 I, we say that. Omega 0 here is square root K over M. K is a positive, is a spring constant, okay, is from Hooke's law. Okay, M is a mass, is also positive, okay. Okay, so what is our solution looks like? Our U1, you can find the fundamental set, right? U1 is a cosine omega 0 t. And your U2 here is sine omega 0 t. Okay. Your general solution can be right linear combination of this, right? Now here they use, instead of use C1, C2, they use A and B. Same thing. They're just constant. Okay. So remember, this is a vibration. Your block is going to be up and down across the equilibrium position. Okay. So if we write our solution in this form, it's hard to tell, to describe such vibration. For example, we want to know the amplitude, the vibration, the frequency, or period of vibration. So it's better for us to write this one like this. R cosine omega 0 t minus delta. Okay. The U can be right either the first way or second way. Okay. The second one, if we use the trigonometric identity, they give you R cosine omega 0 t cosine delta plus R sine omega 0 t and sine delta. Okay. So if you compare the first equation and the third equation, you are going to see, okay, in the first equation, the coefficient of cosine omega 0 t is A, right? In the third equation, the coefficient for cosine omega 0 t is R times cosine delta. So that means my A here equal to R cosine delta. Okay. And the B here, similarly, is R sine delta. Okay. So our displacement function U can be either write A cosine omega 0 t, B sine omega 0 t, or write as R cosine omega 0 t minus delta. Okay. You can write either way. If I give you A and B, you can find R and delta. Okay. You can find that easily, right? If you square both sides of those two equations, you are going to see add them together. A squared plus B squared equal to R squared cosine squared delta plus R squared sine squared delta, which give you R squared. Therefore, you can find R here, the square roots A squared plus B squared, which is amplitude. Okay. So this is the amplitude. Okay. Then you can find the delta. Okay. You just need to divide those two equations. So you are going to find out tangent delta equal to B over A. Okay. So then from this equation you can find the delta. Find the delta, which is what we call the phase. Okay. And omega 0 is called the frequency. And the t equal to 2 pi over omega 0, 2 pi. This is called the period. Okay, now let's look at an example. So here it tells you the mechanical vibration can be described by a second order linear equations, either homogeneous or non-homogeneous, depending on the problems. So if we know how to solve these problems, we can solve the mechanical vibration problem. Now let's look at an example. Okay, in this example, we want to Suppose that a mass weighing 10 pounds, weight 10 pounds, and stretch a spring 2 inch. If the mass displaced additional 2 inch and is set in motion with the upward velocity 1 foot per second. Okay, we want to determine the position of the mass. At any time, at any later time. We also want to find amplitude, phase, period, and so on and so forth. Okay, now remember, for all the vibration problems, your equation can be written like this: m u double prime plus gamma u prime plus k u. If no external force additional, then you got this equation. So for the different problems, you just need to find m, gamma, and the k. In this problem, they didn't tell us, they didn't say they have a damping force. So gamma is 0. That means your equation simply like this. So what we need to do, just find m and the k. Okay, and also initial conditions. Okay. Let's find m and k first. M here, okay, they told us the mass weighing 10 pounds. That means they give you the force. Okay, that means they give you the force of mg. mg equal to 10 pounds. Then that means your mass here is equal to 10 over g, which is 32. Okay. All right, now let's find the k. Okay. Remember, this is like this. This is natural length. Then they hang something with mass there. The stretch here is 2 inch. Okay. So then there's no motion. In the other words, in that case, mg equal to, okay, the gravitational force is equal to restoring force. K times displacement. Displacement is from its natural length 2 inch. 2 inch change to the foot is 1/6. Okay. The unit is important here. mg here is 10. Right? They give us 10. M is 10 over 32. mg is 10. So K here is 60. Okay. Now we have this. We have our equation. M there is 10 over 32 u double prime, then plus 60 u equal to 0. That's our equation. We need to know the initial condition. So we know the initial position. Okay. Equilibrium position here, u equal to 0. They said at the beginning, u is here, 2 inches down. 2 inches down here. U is going down, is positive direction. So u equal to 0 and going down, so it's a positive 2 inches, 1/6 foot. Okay. And we know the initial velocity. They said 1 foot per second. This says upward like that. Velocity is upward, so it's a negative. So it's a -1. So we set up our equation with the initial conditions. Now we need to solve it. Okay. Solve this one, you write as, okay, let's simplify this. This is u double prime. If you divide the 10 over 32, you got this. Okay, if you divide the 10 over 32, you got this. Okay. Then write down is characteristic equation, 192 equal to 0. So your R here is equal to positive and negative square roots of 192i, okay, which is positive and negative 8 square root of 3i. Okay, so this is a situation we got two complex zeros. So your general solution can be written like this. A times cosine 8 square root of 3t plus b sine 8 square root of 3t. Okay. Now we can find A and B by apply our two initial conditions. Okay. So let's take a derivative first. Okay. So take a derivative that give you negative 8 square root of 3a sine 8 square root of 3t and a plus 8 square root of 3b cosine square root of 8 square root of 3t. Okay, now let's apply first condition. U0 equal to 1/6, right? And look at the right hand side. Let's look at the right hand side. Let t equal to 0. Sine 0 is 0. Cosine 0 give you 1. So we got that. A equal to 1/6. Okay, in the second equation, we let u prime equal to 0, give you -1. And the right hand side, t equal to 0, here, t equal to 0. Sine 0 is 0, so you got 8 square root of 3b. Therefore, your b here is equal to -1/8 square root of 3. Okay, so we find our solution. U of t is equal to a, which is 1/6 cosine 8 square root of 3t plus b, which is -1/8 square root of 3 sine 8 square root of 3t. Okay, we solve it. So in this moment, you give me time. T here, I can tell you u. That's tell you where that block is. Okay. However, if you want to know the amplitude of the vibration, in other words, we want to write this like this. R cosine 8 square root of 3t minus delta, okay. What is R? What is delta? Okay. Now we can use that formula, right? R here is square roots A square is 1 over, wait. Right. 1 over 6 square plus B square, which is a negative 1 over 8 square root of 3 square. Okay. That give you a number. That number will be, simplify that, give you 19 over 576. Okay. If you want to find the delta, okay, tangent delta is equal to B over A. Our B here is a negative 1 over 8 square root of 3. Our B here is 1 over 6. Okay. So then you can find the delta there is minus tangent inverse that number. Which is square root of 3 over 4. Okay, you simplify this, give you minus square root of 3 over 4. Okay. So you find the delta. Delta is your phase and your amplitude. This is your amplitude. Okay. What is the period? Period T here, T is your period, is 2 pi over omega 0. Okay. What is omega 0 here? Omega 0 is square root K over M, which is our 8 square root of 3. Okay. So, but put it in there, you can find a T. So we solve this problem completely. And this section basically is application of second order linear equation. Okay. So all the vibrations, mechanical vibration problem can be write in this form. Okay. For different problems, what do you need to do? Just find M, gamma, and K, then you are done. Okay. You end up with solved equation. So, now, let's talk about, in this book, they talk about gamma U prime plus U equal to 0. This is a freight damped vibration. Okay. So, gamma there is a damping constant. M is mass over K here. Okay, sorry. K here, K is a spring constant. Okay. So, this problem, just a second order linear homogeneous equation with a constant coefficient. To solve that, write as R. Okay, this is R plus gamma R plus K equal to 0. Okay. So you solve R here, use the formula. It's a minus B. This is my B. It's a gamma. Positive and negative square roots. B square is a gamma square minus 4. A is M. B is a K over 2A, which is M. Okay. So, now, important essentially, this is gamma square minus 4mk. If this one equal to 0, you got one real root, right? You only get repeated zeros. If this one, you got repeated 0, you say gamma, okay. Let's say R1. Then your solution will be like e to the R1t. So you don't see, once you have vibration, that means you have a sine cosine, right? They change the sign. This one, this function is always have the same sign. Okay, that means the damping is pretty strong. Okay. What situation you will get cosine and sine That case, this one you got less than 0, right? That means the damping force compared with your system is not that strong. Then your solution have sine and cosine. Then you got some vibration. Okay, they call, if this one equal to 0, okay, you solve that, your gamma here is 2 square roots mk. They call this case is critically damped. Okay, that's a critical situation. If bigger than 0 is overdamped, less than 0 is underdamped. Okay, I'm talking about this for you to do your homework.